So right now, as you can see, the time is around 1 a.m. But I guess I just wanted to finish up on the recurrent neural, sorry, not the convolutional neural network back propagation steps. All right, so that's why I just thought I will do a follow-up video. So as you remember, the point that we stopped last time was that here is your, we had the input image, right? You had the input image, and you also, let's say, let me draw the filter with a different color. So you had the filter, the convolutional filter, and often you would have like you will need to do padding because you want the output image to also be the same size. Okay, and then in the forward pass, what you do is you overlap the filter on each of these places, and then you compute the output image using convolution. And because we have done the zero padding, we knew that the output image size also ended up being the same as the input image size, provided we use stride of 1. So let's say this is out. Okay, and the input image, let's say we call it as X, and this is your W, right? So I mean, if you want, we can write other things like X11, X2 like that, but let's just not write the details because we had just discussed this. Now this is in the forward pass, and in the backward pass, what you have is you have the derivatives in the same shape as the output. So this is dl by d output, and we can, this is the input to the backward pass, and what we are interested is in computing dl by dx and dl by dw. Okay, so dl by dw, it is obvious why you need to compute, because you need to do like gradient computation for all the parameters. But why do we do dl by dx? The reason is this could be an output of a previous stage, so this need not necessarily be thought of as the image itself. It could be output of the previous stage. So as a result, we will like to compute dl by dx as well. All right, and in the last class we saw this, we completely understood how to do this. So what we are looking for in today's class is to compute dl by dw. So yeah, so that's what we would like to do, and then what we saw is like when you change each of the parameter, we were asking. So let me just redraw the figure that I drew in the last class. So you have this. Okay, so this is, let's say, x11, x12, x13, x14. Let's look at a small example, and x21, x22, x23, x24, and x31, x32, x33, x34. Okay, so let's say it's just a 3 cross 4 image, three rows and 4 columns, and then we do zero padding. So all the entries are 0. Okay, so now when you are generating the output image, this is the output image. So this is, let's say, O out 1 1, out 1 2, out 1 3, out 1 4, out 2 1, out 2 2. And let's say I have written this as well. So you have this, right? So now what we are interested in to compute is dl by dw11. Okay, so we will look at w11 when we change. What are all the output it changes? So this was the thing, right? We were discussing this last class. I actually did explain how this is, but you all remember, right? So when you are trying to compute out11, your filter, let me just write it in a different color. So your filter will actually be here, okay, and this is the W11. So when you change it, it really doesn't change anything, okay. So the same argument holds when you move the filter along the padding, so nothing changes. The first parameter it actually starts affecting when you look at the W11 is when you are looking at when the filter is over here, okay. So only when the filter is over here will you get that X22 is changing, okay. So when you change W11, okay, X22 changes. So let me sorry, not X22 but out22. So let's write that out22 is equal to X11 W11 and plus whole other things that we don't really use, okay. So when you try to take DL by D W11, so you will get DL by D out 22 okay. So you remember the input was the gradient matrix. So the gradient matrix input I am going to write here. So this is DL by D out, right? So here it is the same size as the output image, but I will write the notation just O11, O12. This is the output gradient that is actually the input to this stage for the backward pass, okay, like this. So now so as you can see when you change X11 out22 changes, okay. So that means the effect that manifests in the final DL by DW1 is through out22, okay. So this is equal to X11 out 22, okay. So that is what it is. It is X11 X out 22 plus, okay, when you slide it from this position, when you slide it to the other position, so let me again draw it here for your benefit. So when you bring this the filter over here, then again X23 is changed, and that is affecting this fellow. The through X12 it is changing X23. So the same way X12 sorry, this is not out22, remember, so it is O22, because the output gradient we are actually calling it as O22. So that's what it is. So X11 O22 and then X12 O23 X12 O23 plus, so when you move it once again X13 so this one and then this one. So this entry gets changes, okay. O24. That's about it in for this simple example, okay. So this is what we saw, and what I said is that we can actually treat this output gradient. So let me try to say how this can be done using a simple step, okay. So let's just note that this is correct. So when you take the output gradient, so let's now let me again use the same color. So let's say you have the output gradient O11 O. I would like to maybe write it little small, maybe not, okay, yeah, this is fine. So O11 O12 O13 O14 O21 O22 O23 O24 and then O. I was a little ambitious in right, the gap was too less anyway. O31 O32 O33 O34, right. So then what I said is that you put a padding. So let's put a padding of the same size as your input image padding. This is your gradient vector, mind you. And then what we said is that you take the original image. Original image, remember, is the same size of this thing, and then you overlap over here. So when you overlap the original image over on top of this, and then you try to do a filter. Okay, so you do this. Okay, so and then once you so the original image is the same size as this, so that you should remember. So though it is not very obvious, this box and this red box are the same size. Okay, so it's not very evident that it is, so maybe for the sake of making it 100% obvious, so let's make that. Okay, and then you are going to do this is your original input image, so this will be x1, right? x11, x12, x13, x14, x21. Okay, so here it is x22, x23, like that. Okay, so when you take this entire thing, the claim is you will get, so if you repeatedly do this, you will get a value whose size is the same as your filter. Okay, so this will be dl by dw11. So just check when it is in this position whether you get, right? So it will become you can see. So this is so what did I do? So when I change, yeah, so let me just pause briefly. Okay, so I was just thinking that when you do convolution with this and this, it doesn't match, right? So as it turns out, you shouldn't pad you shouldn't pad the output pixels. So you should pad only the input. So let me just redraw this by taking a small pause. Okay, so this is original input padded image. On that we are trying to now convolve with the output this matrix, right? So when you first time put it on top of this, you will get this operation. So just let us check whether you actually indeed get this. So x11 times, so this is O11, so let me write this: O11, O12, O13, O14, O21, O22. So x11 times O22, x12 times O23, x13 times O24. Okay, so that will give us this. So similarly O32 times x22 and so on. So yeah, if you continue, the same idea continues, you get this. And this you will next when you move it to the aligning with the image, you will get dl by dw12, then you will get dl by dw13 and so on. Okay, so you can always see, so when you are in the extreme corner, you will get the extreme corner here. When you align with the thing but one row above, you will get this. And when you are pushed it to the extreme padding, right? So their padding is this is some like thing from the previous thing which I didn't clear off, but you will get the same size. So that one point I wanted to make. All right, so I know this is not been the most clearest explanation, but I hope you can follow and you can build up on this based on this idea. Okay, so this is one thing. So this now finishes dl by dx as well as dl by dw. Okay, so let me just see what else we need to talk about the forward and backward path operations. Okay, so let me take a pause here. Okay, so the only operation that is really left is what is called as a flatten operation. So there is other things like max pool, average pool. So this is you can just check on your own how to do the forward pass of max pool, average pool. Okay, let me just say, so in max pool you have something like this. Okay, so you want to basically reduce the dimension of the image that is there in the convolution layer, suppose, and there are some bunch of numbers. So in max pool, what you do is you take, let's say, some region like this, and you choose the max. So when you choose the max out of 4 things, the dimensionality becomes small. So this is called as the max pool. The average pool is, instead of taking the max, you take the average. Okay, so forward pass is clear. Backward pass is, you want to compute the gradient here for max and average. For average, the gradient is simple. It is just the average of the gradients. For max pool, what it would be? Yeah, I will just leave it for you to think about. Okay, it's not too difficult. So this is the other operation. Then finally, the last thing that is there here, which is called as flatten. Okay, so what flatten does is, given your input pixel, okay, so what it does is, input image, it just makes it into one single row. It takes each of these numbers and puts it in a row by row fashion. So like this. Okay, this is the flatten operation. So forward pass is pretty clear. You just have to reshape your input and you get this. This is the forward. Okay. In the backward pass also is pretty obvious. So you will get your gradients in this column vector form. In order to put it in this form, you again have to reshape it. So forward pass is also reshape and backward pass is also reshape. Okay. So these are all the things here. So I think only thing left now is to talk about channels. So let me just do that. So the last thing that is there is the channels. So let's just talk about that. So as you know, if you look at RGB images, okay, so there will be, we can think of that as 3 separate images with the red intensity, the blue intensity, and the green intensity. Okay, so each image is actually can be thought of as having 3 channels. Okay. Now, when you put a convolution filter, given 3 channels, suppose if I am interested to have let's say 5 channels here, right? So I want to have 5 channels from 3 channels. So the input channels is 3, output channel is 5. What I will do is that for the first thing, okay, for first input channel and first output channel, there will be one filter. So this is one filter 1, and first input channel and first input, so this one R, and then to get this there is 1, and then second input channel and the first output channel there will be F2, and then third and first output channel there will be F3. So basically 3 into 5, 15. So you have like this, right? So this is 1, 2, 3, and then 1, 2. So first to 2, second there will be F4, like this. Okay, 2 to 2, F5, like this. So what you do is, with this filter you convolve this and put it here. Okay, and with this filter you convolve it and you add it to the previous result. So that is the whole thing about channels. Okay, so I will leave it as a homework for you to figure out the forward and the backward pass. Okay, so in the forward pass you accumulate the results. Okay, accumulate. So this is it. So these are the channels. So these things I would like you to implement. Okay, so one practical thing for implementation, practical consideration. So if you try to convolve by writing for loops, right? So for here, if you want to do for this kind of convolution operation using for loops, it's going to take forever. So what you need to do is you need to use you need to extract the relevant thing, extract the relevant regions, and extract the matrices of the relevant region, and do not matrix multiplication but element wise through the matrix thing, right? Matrix element wise multiply. Okay, so so that if you do it, the speed of execution will be fast. So this you need to do when you implement this from scratch. Okay, so that's about it. So let's stop here.